Okay, the next definition, kind of the one that corresponds to injective, is surjective. That's what we're going to define now. So, the function from f, from a into b, is surjective, and I frequently use the word onto instead of surjective. Remember what that means? It means that every value in b gets mapped to by something from A. So I'm going to draw a picture, and then maybe we can figure out how to, or maybe you can figure out before I write it, the definition of a surjective function. So A, B, F. Well, the way I draw it anyways, is there has to be, for every single point in B, f of a, there has to be an a that maps to it. So I usually draw it. Let me put like that, f. I usually draw it like this. And notice I made b look larger than a, and that's fine. But I would do something like almost like a comb, just kind of making it look like to the person looking at the picture that there's not a single point over here there's not a single point in B that doesn't get mapped to. Okay? After we write this definition, I'm going to make another statement about how a graph would look. So, would have been, maybe it would have looked nicer if I made A look bigger than B, but this is still valid. Okay, how do I define that? A is on, or F is onto or surjective. How do I say if every point in B gets mapped to by a point in A? I could write that out, but it's very wordy. Let's use a mathematical notation here. Just in case, I'm not going to write it over there, just in case I run out of room. If for every b, little b, that's in this set, so this is an arbitrarily chosen point, there exists an A in this set such that, ST is such that, f of A equals B. This means that there is a point in A mapping to that B that we chose here. And this is for every B. So every single point in B is getting mapped to. That's the definition of surjective. Now, let's suppose that A and B are finite. In other words, they only have a finite number of elements in them. So it's not like one is the set of integers and one is the set of real numbers. Let's say that A is equal to m. M is just a natural number. And B, number of elements in B, is equal to n. M and n are both positive integers, natural numbers. Can we say anything about A and B if f is a surjective function? I'll tell you, yes, there is, and it's a big statement. It's let's do 3 and 4. Say m is 3 and n is 4. So A looks like this, those 3 points, and B looks like that. Is that possible? If f is if f is a surjective or onto function, well, let's draw a picture. That one can get mapped to, but A can only get mapped to 1 because it's a function. That one could map to there, that one could map there. We've got one left over. It's impossible. So the requirement would be if A and B are finite, then we have to have the number of elements in A less than or greater than or equal to the number of elements in B. If you had 1, 2, 3, and 1, 2, no problem. That one maps to that one maps to that, and this one maps to that. That's a beautiful function. It's not 1 to 1, but it is on to. All of the elements in B are getting mapped to by an element in A.